Hi everyone, welcome to this session. I'm Chuan Hua Chang from AndesClarity. I'm here today to tell you about AndesClarity, a performance visualization tool for RISC-V vector processors. The agenda will be first an overview of AndesClarity, second an example processor pipeline with vector processing unit. Third, a program analysis example using AndesClarity on the example processor. And at the end, a summary. Let's start. Let me introduce AndesClarity now. AndesClarity is a pipeline visualizer or analyzer for AndesV5 processors. It provides program performance data and highlight execution bottlenecks. It is ideal for complex processor pipelines such as Andes Core NX27V vector processor. The tool's performance data is from the execution log of Andes instruction set simulator, and it is integrated into the AndesSci integrated development environment, which provides various features such as easy debugging, profiling, and link to source code from RISC-V instructions. The tool represents performance data graphically on high-level instruction per cycle IPC metric and on instruction execution pipelining flow, and shows data dependencies and resource usages. There are three use cases for this tool. The first is for algorithm tuning. A user can identify bottlenecks from pipeline stalls or resource usages and try out different optimizations. The second use is for compiler improvement and flag tuning. If the compiled code generated is not efficient. And the third use is for processor configuration exploration and help users to discover potential microarchitecture improvement. In AndesClarity, there are two main interfaces. The first is a performance viewer, which displays IPC instruction per cycle or OPC operation per cycle information. The second is a pipeline stage viewer, which can be shown instruction-centric or resource-centric. The later slides will tell you what's their difference. The performance viewer is a timeline view of the instruction per cycle or the operation per cycle metric. Most people should be familiar with the metric of instruction per cycle. As for the metric of operation per cycle, it is designed especially for vector instructions. A vector instruction has VL, that is vector length operations, instead of one operation. An example OPC window picture is shown here. On this window, you can zoom in to find more detailed metrics information. To find vector instructions, you can see where the OPC number is greater than 1. The Instruction-Centric Pipeline Viewer displays the instruction code sequence and the instruction execution pipeline flow as shown in the picture. The lower part of the window shows the microarchitecture resource usage information. You can notice that a focused instruction in the window can be highlighted in blue. This is the Resource-Centric Pipeline Viewer. The Resource-Centric Pipeline Viewer displays the pipeline stages in processing units versus their occupancies by the instruction execution flow as shown in the window picture. The lower part of the window also shows the microarchitecture resource usage information. This view is suitable for instructions that pass through multiple processing pipelines that will be overlapped in clock cycles. The instruction-centric view can only show one of these multiple overlap stages, but the resource-centric pipeline view can show all of them. On the pipeline stage viewer, not only the focused instruction can be highlighted, but both the producers and consumers of the focused instruction can be highlighted as well. This will help a user to easily find dependencies between instructions. And pipeline stores in this window are displayed in colored square. If you put your cursor on a square, a small tooltip will show up to display instruction information. For a colored square, a stall reason will be displayed as well to help a user identify the performance issue. Now, let's look at an example vector processor pipeline so that we can use it as a reference for program optimization discussion later in this presentation. This is the pipeline diagram of AndesCore NX27V vector processor. It shows the 5 main pipeline stages of the scalar pipeline, along with the beginning stages of the vector processing unit pipeline. You can see that both pipelines are connected through a vector instruction queue, abbreviated as VIQ, and a bidirectional data path for data movement between these two pipelines. There is also a custom instruction pipeline that can be communicated to a custom coprocessor. And we also have a streaming port that get data from the custom coprocessor. Now, after looking at this example processor pipeline diagram, now we will talk about an example of using AndesClarity to do code optimization on the above vector processor. This code is from a forward DCT algorithm. The initial vectorized code contains a repeated code sequence as shown here. It does a vector multiplication and then a vector reduction sum, and then move the one reduction result to a scalar register and use a scalar store to put it in memory. The average performance of the sequence is 16 cycles per iteration. From the AndesClarity display that will be shown in the next slide, the developer found that the scalar store instruction is waiting for its data from the vector processing pipeline and is blocking later vector instructions to enter the vector processing unit. The developer learn that frequent interaction between the scalar and vector pipeline is not good. Now, let's look at the AndesClarity display for this code sequence. From AndesClarity display, you can see here that the blue colored square of the store instruction shows the store cost of waiting for operand, which is produced by the vector move instruction, and which takes several store cycles. And you can also see that the vector instruction queue does not have many vector instructions in there from the lower part of the VIQ resource usage display. From the above discovery, the developer decided to change the scalar store to a masked vector store to put the reduction sum result to memory. After this change, now the average performance of this code is improved to 8.3 cycles per iteration, and he or her found that the vector instruction queue is full for this change. But it seems that it is not efficient to vector store just one element. From the AndesClarity display, we can see that the VIQ is full most of the time now, which is different from the previous picture. But it is not efficient to just vector store one element. And additional add instructions need to be added to calculate the next address for each iteration. This causes additional cycles for the iteration. In the third attempt, the developer decided to use a v-slide-up instruction to gather the reduction sum results into a vector register instead of storing them out one by one. For this change, the performance now becomes 6.75 cycles per iteration. From the pipeline display, the user found this time that due to strong dependency, the functional units overlapping is low, and the vector multiplication instruction of the next iteration will be blocked for several cycles. This is the AndesClarity display for the third attempt. You can see that the performance is not as good as what the developer would expect. You can see multiple stores for the multiplication, the vector multiplication instruction in each iteration. To increase the vector units overlapping, the developer decided to reduce the instruction dependency by interleaving 3 iterations together. You can see the code sequences on the slide. And use additional 2 pairs of registers. After the change, the performance is improved to 6.1 cycles per iteration. The utilization of vector functional units is increased, but the iteration latency is dominated by the non-pipelined reduction sum instructions. At this time, further improvement needs to come from more drastic algorithm change. We can see now the pipeline diagram becomes more compact with less store cycles. And you can see the timing is dominated by the non-pipelined reduction sum instruction in the center of the window. By using such a tool like AndesClarity, a user can learn the processor microarchitecture characteristics, the execution latencies of instructions, the interaction between scalar and vector pipeline, especially on data movement between them, and the reasons of lost performance and also the resource utilization and data bandwidth under different code sequences can be observed. In summary, AndesClarity can help a user to quickly understand the bottleneck of his or her code and easily be familiar with the microarchitecture of the target processor and to discover potential enhancement to improve the application performance. AndesClarity is a powerful tool for vector processor such as Andes Vector Processor NX27V. And this tool is integrated inside Andes IDE for easy vector application development. Thanks for attending this presentation. If you have any question, you can start to bring them to me now.